for another episode live of Dan Does Data. Tonight we're going to be continuing the line-by-line series last week. That seemed to be popular. Last week we went through this fully connected feed, .py, which is the TensorFlow tutorial just for getting your code kind of set up to download, read in, and I think actually run the model for this mnist digit classification. So I thought today I'm just going to go ahead and go through the mnist.py companion file that just literally specifies the model. And we'll end up building the same model again, except this time I'll be focusing on, what does the model actually look like, instead of how do you actually get the data in. So sort of the actual machine learning part of the problem, as opposed to the generic part of the problem. So the way you get to this, if you're at tensorflow.org, you can go over to tutorials, and it's not obvious. You might think it's under beginners. You might think it's under deep mnist for experts. It's actually under TensorFlow Mechanics 101. And if you go to train the model, if you go to tutorial files, then it gives you those. And you can download those directly then. You click on that, it takes you to GitHub. You can click on raw and then just save page as. That's how I do it anyway, but you can do it however. Alright, I've already downloaded that file and I've got it opened up over here. It's copyright Google. Thank you, Google, for letting me borrow this. We're also going to need fully connected feed.py, because this will be an important component. You might have noticed I've adjusted the terminal split here. If you think this is too much to the left, let me know. We're going to find out. I mean, normally the IPython is just for running things, so it shouldn't be too much of a deal. Alright, so right now this is back to fully connected feed. This is how we read in data. So let's just go ahead and do that. Make sure we do that. We're running Python 3, of course, so I'm not worried about this future stuff. There we go. Actually, hit the set background. Oh yeah, I got my own. Oh, that's not what I want. Got my own. I had set my own color scheme. There we go. I don't know if that's actually better or not. I like it. It's a lot of purple. That is an unusual amount of purple. One second. Dark. No, not dark. Background light. There we go. Okay, no, that's an unusual amount of red. But at least things don't highlight in red. So I'm hopeful things will highlight a little better. A little more consistently. I don't really care about syntax highlighting while I'm personally highlighting something. Alright, let's go back to fully connected feed just to get things set up for what we got to do. We defined our flags. I'm going to turn off auto indenting because we're sending over code that's already indented. That was really fancy. That was really good. Is this? I don't think I ran this yet. That is a whole lot of blue. Oh my goodness. I did not expect there to be that much blue in my life. Let me switch over to chat here, make sure I'm not missing anybody. Okay. We did do a val. Run training. Well, we're going to use run training in a loose sense of the word. Oh, this isn't going to work. This is not. Run fully connected feed, import star. That's how we're going to do this. Argument, learning rate, conflicting screen, -- learning rate. Let's just kill this. Bring it back. Much better. Okay, now I've got all those functions. That's what I really wanted. So now we should be able to actually run the code with just run training, for example. Okay, but we're talking about mnist tonight in the actual building of the model. let's start as before, all the way at the top. There's a license here for Google, so make sure you respect that if you're going to steal their code directly. I'm not putting this in any kind of product, so this should be fine. Builds the mnist network. So this tells you it implements the inference loss training pattern for model building. So I'm interpreting this to mean we're going to build what the model is, the inference. We're going to specify what the loss function is, how we penalize our model for when it's wrong. And the training, that is the optimizer that is used for actually training the model. But we're not supplying any data here. Oh, in fact, they describe them. Inference builds the model as far as required for running the network forward to make predictions. AKA, we're going to specify the hidden layers of this network and the final softmax activation function to get probabilities out. Probabilities of whatever digit we're talking about, that is, loss. Adds to the inference model the layers required to generate loss. We're going to compute how wrong we are in a statistically responsible way, I think is the best way to put it. And of course, training adds to the loss model the ops required to generate and apply gradients. That is, we're going to tell our model how, given some data and given a computed loss function, how to adjust our weights to be more correct. Generally, that's something like gradient descent or the atom optimizer or AdaGrad or a whole bunch of other things. This file is used by the various fully connected star.py files and not meant to be run. Yeah, well, that's interesting. Used by various fully connected... I didn't see other. So, it's used by fully connected star. I didn't actually see other fully connected feed. Maybe there is another? Fully connect... That's not one there. Is there another one that exists somewhere? Serving. Interesting. Model architecture. I don't know. Maybe they exist. Let's check the GitHub page actually. Examples, tutorial, mnist. This just has fully connected feed. There's only just one. Maybe they intended there for be more than one. Alright, well that's fine. Okay, as before, let's walk through these first lines. This is the same as it was last week, but I'll go into them again in case you didn't see last week. So from future, import absolute import. Again, this is just a Python 2 thing. If you're using Python 3, it's not going to matter. Absolute import, I believe, is what allows you to from dot import foo. So we don't need that. Similarly, from future import division in Python 3. In Python 3, if you say 1 divided by 3, you get an actual 1/3 estimate. In Python 2, you would get 0 because it gives you the, by default, it chops off the fractional part. It does the integer division, so to speak, which you can get in Python 3 if you do //. It's all about what you want. So they're assuming is saying, okay, if you're in Python 2 or if you're in Python 3, these things don't do anything. But if you're only in Python 2, they'll do the right thing. And from future import print function, of course, the Python 3 print function is amazing, namely because it's a function. You can print to certain files. You can import separators between the values that you're printing. You can specify a different end value. It's super good. So if I print 1, 2, 3 by default, I can do that. And if I say, oh, I want my separator to be a comma, you can put a comma instead of a space in between them. There's better ways to do this. But you can, that's something nice to have. If you got a particular end, for example, I want 2 new lines instead of just 1 or none. Pretty cool. And you can print to a file, which I often use when I'm printing to standard out. So I don't have to do like file.write. I can just print. Flush being a command, whether to forcibly flush the string. So your terminal or your IPython session probably has a buffer that it's filling up when you print things. And if during the middle of a script you tell it to print, but then the script like crashes or something ends, if you didn't flush, you might not actually get to see that output. Flushes the buffer is the terminology, and so actually pushes out all those before doing something else. Okay, math. Let's import math. Math is a very common Python module doing lots of nice things. Here's all the things you can do. Lots of common trigonometric functions, arc, cosine, all your sine, cosine stuff is here. You've got the ceiling operator, and I think you have the floor operator. So floor sort of rounds a decimal number towards 0. That is down in general, if you have a positive number. And ceiling rounds you up, away from the 0. So if you have a negative number, you get more negative. It's important to remember. You get some nice constants like e. You got the ear function, you got the exponential function, you can take vectorials, other things like gamma functions, you get more constants. You get not a number, special, log, which is important. And you can just ask, are these two values close? Which is nice if you've got some numerical precision error. Relative, and it asks, maximum difference being considered close. Yeah. Maximum difference being considered close regardless of the magnitude, relative to the input of the input values. Interesting. I don't actually use this that often. It's just interesting. That's cool. And is not close to anything, even itself. Inf and negative int are only close to themselves. Cool. So if I say 0.999999999999, math.is close, that and 1. Is that true? Yes. Whereas if I didn't have that much precision, those aren't that close. We're probably not going to be using it as close, but that's just... I felt like trying that out, and it's my show, so I get to do what I want. Of course, here's the money. Import TensorFlow as TF. Boom. I got to remember to click the button on Reddit. Let me do that. Bam. Okay. Welcome, Redditors. All right, let's continue walking. We just imported TensorFlow. If you're using TF, that's just shorthand. I like that because it's tensor and flow, T and F, pretty simple, standard. All right, num classes. This should be pretty straightforward. The mnist dataset has 10 classes. You've got 10 digits. 0 is the first one, 1 is the next one, and so on and so forth. Very computer science. It's in all caps here just because this is a constant, and programmers like to put constants in all caps, but that's not required. If you like, you can pretend you're programming 30 or 40 years ago and your compiler only respects things in all caps, whatever you like to do. Image size. Okay, the mnist digits are only 28 by 28 pixels, so they're very small pictures. Let's see if we can actually take a look. Is it possible to take a look at one here? Placeholder inputs, feed dict, run training. Data sets, input data.read data sets. I wonder if I can just run this. There we go. Datasets.train. TensorFlow.contrib.images. Okay. Let me import matplotlib.pyplot as plots. Oh shoot, no. PLT. PLT.ion. This is just to help us plot some stuff. Let's look at, I don't know, -4. Dot reshape, of course, because it's going to be 28 by 28. Let's see this blow up in my face. Oh, that didn't work. Right, because I'm not plotting this. I want not a plot, I want a heap plot. Which you do with p-color or p-color mesh for a faster version. I think p-color mesh is nominally not exact. So that's kind of interesting. I think actually I want image show. Yeah, there we go. So image show kind of blurs things for you automatically a little bit to make it look nicer. And it flips things to be in the correct axes. So that's a 3. If you have CMap equals plot.cm.gray. There we go. So you can also get black and white, or I think TensorFlow proper in their tutorial they show you something like this. Maybe not with this fuzziness. That's just the image show trying to be nice to you. I don't know why I have all these weird libpngs yelling at me, but things seem to work just fine. So not curious why that. We have a question. Recently moved to TensorFlow from MATLAB. Most people in college do not use it. Should I stick with TensorFlow or go with alternatives? That's an interesting question. I would say so MATLAB and TensorFlow serve very different needs. MATLAB is a very general sort of high-level scripting language. It's used by a lot of engineers for things like that. Sort of similar to Python. I consider Python even more general. MATLAB is for doing numerical computations mainly, I think. Whereas TensorFlow I sort of think of as more specifically a machine learning library, but machine learning in the sense that anything you can define with a graph computation. So if what you're doing easily fits into that paradigm of a graph computation, I would say sure, go ahead with TensorFlow, or you might try one of the many other alternatives like Theano, or if you're looking for something higher level, try Keras. I've heard good things about lasagna. I'm probably going to be looking at that in the future. In general, I would say use both. Use everything. Personally, I use Python because I love Python. I'm familiar with MATLAB. MATLAB was my first, I'm going to say quote-unquote real programming language. I used BASIC or QBasic. I think, was it in junior high? Yeah, I programmed some silly text adventure game. And then of course there was a calculator basic. I did some of that too. So I'm going to type it back to him. Use both. TF for machine learning and MATLAB or Python for general computing. All right. I always appreciate questions from the chat. So if you have anything else, shout it out. Honestly, the live part of this is more important than the recorded session. All right. We're talking about the image pixel size. We took a look at the images. They're 28 by 28 pixels, not very much. And so, of course, you need to compute how many total pixels you have, which is 28 by 28, which is to say image pixels. Because for a very simple model that isn't convolutional, that is, just considers each pixel independently of all the others, then you want to unroll that all to be 784. Another clarification from Nomad Jake. He's dealing with time series data. So if you're dealing with time series data, you want to build a time series model. TensorFlow has those. I fiddled with those a little bit off stream. I'm actually not a super big fan of how they handle it. If you're doing some kind of neural networking, recurrent neural network business. But if you're doing a more standard, let's say classical approach, then I would stick with whatever that is. I think ARIMA, that sounds familiar. Yeah, I would open up the statistic literature and worry about what kind of model you want to build first. And after you've sorted that out, then you can sort of decide what kind of language you want to use. And chances are the language you want to use is one that already has a library that implements your model. So if you're doing recurrent neural net, maybe TensorFlow is good. I had pretty good luck with Keras, which you can use on top of TensorFlow, or Theano, whatever you like. All right, let's continue with this. We've got inference. We're building a function. What are we doing with this function? Build the mnist model up to where it may be used for inference. They say inference. What they mean is we're actually going to specify the neural network here. So what do you got to do? You got to put in your images, your data, that is. I think this is the actual data. We'll see that in a second. No, this is going to be the placeholder, TF placeholder variable of the images. Hidden 1 units. This is how many nodes we have in our first hidden layer of the network. So this list layer is going to take in all the pixels as input and is going to spit out this many values. Similarly with hidden 2, we're sort of automatically specifying two hidden layers and only two. It's going to take in however many from the first layer and it outputs however many you have here. And these go into the 10 sort of scoring functions that make up the output. Sorry, that make up the logistic regression output, the softmax linear business here. All right, I am going to just grab a drink of water real quick. I am parched. Oh my goodness. Okay. Hopefully that wasn't so bad. All right, continuing on. Let's start right away with hidden layer 1. So they like to use this with tf.namescope. This is mainly so you can refer to these nodes later in a relatively easy way. If you saw my old video on skflow and getting the hidden weights, this is what made that possible. Also, it's because they're going to name things weights, use the same variable in two different places. So they kind of have to say, hey, by the way, this is in a different scope. So you can also think of this as saying, instead of this just being called weights, this could be W1. So what are we doing? In this scope, we got to make some weights. So this is where you actually define those nodes. Or excuse me, this is where you define the weights that are going to be associated with your nodes. These are the things that you're going to train. So we say tf.variable, because these are things we're going to change and train. You're going to use tf.truncatedNormal. Truncated normal gives you sort of normally distributed initial values, but not too extreme. That's the truncated part. It cuts them off. And the question is, how many do you need? Well, you've got image pixels input features. Each pixel is a feature, and you've got a bunch of different data points. And you've got this many nodes. Each node gets to see all of the inputs. So really, you can think of your weights as a single matrix of image pixels rows and hidden 1 units columns. The standard deviation business, this is just, again, defining how you initialize. So they're saying 1.0 divided by this math.square root. Basically, you are scaling to your number of inputs. And I think this might not be exactly LeCun initialization, but it's pretty close. And it's not going to make a big difference here. We do this float business because image pixels is an integer and math.square root. I don't know why. I should be able to say math.square root of 10 and it spits out a float, which is 10.0. I don't think that's really a big deal. Well, I'll tell you what. Math.square root 784 as opposed to float. I mean, I get a float back either way. This might be if you have a large number of image pixels or input features, say. Then it would be important to convert to a float, because math.square root might try to do something different if you've got a float versus an integer. Note that, of course, we get 28 back because our pictures are 28 by 28. So, like, in this case, we knew that ahead of time, but we're computing it back again. And we're calling this name weights. That's only going to be relevant when this is writing to the log file, which we'll get to later, maybe not. So similar to the weights, in addition to every pixel being a feature, we like to add one additional feature, which is just always 1, the constant feature. This handles if some classes in your outputs are just more popular than others. In a basic logistic regression, that's what this handles. In this case, we are just going to do just like we did above, except we're going to initialize it to zeros. How many zeros do we have? We get a bias for every node, because every node sees all the features, remember. And you have to put this in a list context, because you're sort of passing in an array. You could have an array of biases, but that's not going to make sense, as we'll get to in just a second. And of course, this is called biases for the logging. Okay, hidden one. So you've got all these weights, right? What do you do with the weights? What makes it a neural network? You use the weights and you bang them against your images. So each node, which a node here is sort of like a row of this weights matrix. And you want to take that row and sort of like multiply it by all the input features, right? Such that you have a weight for each pixel for each node. And you can do those all at once efficiently in linear algebra with tf.mateMul. It's just a matrix multiplication. This is why you do your weights as a matrix, because your images are going to be a matrix of your num data rows, or num images rows, times 784. And your weights are 784 by hidden 1 units, say 10, so you're going to end up with num images by 10 factors here. And biases, of course, is just, it's going to be 10, whatever in this case. And so you just add that to every output here. So you've got this matrix multiplication that shoves your input through each node. You add the bias term to each node. Again, because there's a sort of a hidden 1 times here. There's implied. And then what do we do with this new value coming out of the node? We shove it through this RelU activation function. So what is RelU? RelU is just rectified linear. Let's see if I can whip up some stupid data. Oh. Yeah, so we're gonna want num.zeros 10 plus num.a range 10. Let's just do that. Import num is np. Oh, that's not gonna work. That's not gonna work at all. Numpy.concatenate is what I want. I'm just whipping up some RelU activation function business. Only length 1 arrays can be converted to Python scalars. Do you want a list? Is that what you want? There we go. Yeah. Okay, imagine for a second that this axis is actually at 0. This is actually centered at 0, but so negative values are all 0. Positive values are just whatever they are. So it's linear, but rectified is this business. So you only let positive things through, everything else gets shoved to 0. That's rectified linear. It's very popular in machine learning, and it comes built into TensorFlow, which is nice. So you do this hidden 1 thing, you save off those values. You've got, say, 10 output values, whatever they are, whatever hidden 1 units is. After doing all that baloney, you say, okay, that's my first hidden layer of the network. I've got 10 nodes. I took my 784 inputs, did this transformation to them to get some new features, 10 new features. And you say, all right, what do I do with those? Let's do it all again. So you make a new scope, hidden 2 for our next layer. You make a new set of weights, and now you've got 10 inputs from the previous layer, and you've got maybe, I don't know, 20 outputs from this layer. So that's hidden 2 units here. You initialize the exact same way. Just keep in note, here, you've got hidden 1 units is what you're scaling by. You're always scaling by the number of inputs to the layer. This is just called weights again because it's in a different scope. You're okay. Your biases work exactly the same way. You've got hidden 2 units, hidden 2 nodes on this layer. So that's how many bias terms you got, 1 for each node. And your hidden 2, again, is just using RelU activation. Again, we're doing tf.matrix multiply and we're adding in the biases. It's the exact same type of network. Instead of ReLUs, you could have sigmoids instead of. Generally, you usually keep a bias term around, and this is the standard method of dealing with your weights. Your weights do something linear, and then your activation does something nonlinear. All right, so now you've got some new set of outputs. You've computed some new set of wild and crazy features. So now you've got 20 features for every image that are some strange transformation of all the input pixel values. Well, what do you do with those? Now you shove those through traditional logistic regression modeling. So in logistic regression, you take your input features, you find a weight for each feature for each class. So in this case, there's 10 classes, so we're going to have like 20 input features times 10 classes weights. This works very similarly, but not exactly the same as a sort of hidden neural network layer. Very, very similar. In fact, the weights we're going to initialize exactly the same way. With now hidden 2 units, that's how many input features we have. You can sort of think of these input features as just transformed inputs of all the pixels, and now we're just running logistic regression on those. So you don't even think of them as pixels anymore. They're high-level features. You have biases, just like you do normally. In fact, one of the biases should actually always be 0. Here you initialize them all to 0. But in logistic regression, it doesn't really make sense to have a bias term for every single class, right? Because one of them you just sort of is going to be the baseline, and if you can define the other 9, you can define all of them relative to each other. So there's sort of like an extra parameter here that you don't need. So in the ideal world, one of these should always be 0, but it's much, much easier to code if you just say, do them all. Okay, and they're saying logits here because they're not yet returning the probabilities. They're just sort of, you can think of each logit as a score for a class. So you've got all these pixels, you shove them through your hidden neural network layers, and you've got these weights and biases now. So to compute your score for that being a particular class, you hit those hidden outputs with your weights, your logistic regression weights, add your bias terms, and you get a score for each class for a given image. So you say, well, this is a score of 20 for a 0, and a score of 30 for a 1, and a score of -5 for a 2, and so on and so forth. And that's what this is returning. That's what logits is right here. All right, let's keep going. I guess I didn't really need this. I Pythoned it all tonight. So that's that function. That's just to return the logits, the scores for given classes. Then they define the loss function. Pretty simple. Calculates the loss from the logits and the labels. Again, this is just how wrong is our model. It's not exactly the accuracy. It's a little more specific than that. So to do this, you need your scores, your outputs of your model, and your labels. You need to know what your data actually was. Someone needs to have looked at it and says, oh, that's a 0, that's a 1, or something like that. And they're saying that your input logits come in batch size, come in unclasses. So batch size is just going to be how many images are you looking at once. So I think typical is like 32 or something. Typical things like that. If you're only looking at one image at a time, it's just 1. Num classes, of course, 10. And similarly, your labels, you better have a label for each logit, each set of logits you're looking at. And loss, they're saying the loss tensor of type float, how wrong you are in a statistically responsible way. Maybe that's going to be my new catchphrase, statistically responsible. Okay, labels. So you take your labels, whatever they are. I think, it's saying you have labels of type int32. And I believe these labels are going to be, they're not fancy, are they? I was thinking labels were 1 hot. Hang on. So again, you might have a label. If your labels are 1, 2, 3, 3, versus labels 1 hot would be 0, 1, 0, a whole bunch of zeros, and then 0, 0, 1, a whole bunch of zeros, yada, 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 yada. So you stick a 1 in whatever position is associated with that label. So a 0 puts a 1 in the first position, a 1 puts a 1 in the next position, a 2 puts a 1 in the next position, so on and so forth. But it's not clear here. But it looks like if the input is just batch size, then you put in your actual labels, which is interesting. I didn't realize you could do that. Well, I knew you could do that, just at some point you have to compute. You have to sort of get them in a format like this to make the computation simple. Alright, so but first they just convert it to a 64-bit integer. And I have to imagine this is just a numerical stability thing. 32-bit integers are great. The problem is they only get so big. They're about 4 billion. And if you want signed integers, which I think these would be, you'd only get half as many. 2 billion. There was a very popular YouTube video by Korean pop star Psy. He got more views than a 32-bit integer could hold, and YouTube had to actually change their database to use 64-bit integers to hold all the views that his video got, which is crazy. The 64-bit, however, should last a long time. Long time. That's I'm not too worried about that running out. Video gets more views than that. We've got bigger problems. Okay. So you convert your labels just to 64-bit integers. And then here's the money. Here's where it's coming in. Cross entropy. So TensorFlow has built in, what is they calling this? Sparse softmax cross entropy with logits. Oh, jeez. tf.nn is neural net, of course. Sparse softmax. What do they say about it? Whoa. Name X entropy. Oh, so this X entropy is just for logging purposes. Again, logits and labels, okay. Probably error in discrete classification tasks in which the classes are mutually exclusive. Each entry is in exactly one class, right? So we're classifying into one image or another. For example, each CIFAR 10 image is labeled with only one image. An image can be a dog or a truck, but not both. That's actually a really good explanation. Probability of given label is considered exclusive. Soft classes are not allowed. Right, so your labels have to be all 0 or 1. You have to be explicitly in one class. Let's provide a single specific index for the true class for each row. So by single specific index, that's where they mean it's not in one hot format. It's in class 1, it's in class 2, it's in class whatever. So what's the sparse part about this? SOPS expects unscaled logits since this performs a softmax on logits internally. Right, so we'll get into that in a second. You can scale all your logits into actual probabilities. This thing is saying, don't do that. Don't give it those because it's going to do that internally. Do not call this out as it will produce incorrect results, which is interesting. The output of a softmax. I'm not sure. So like if it's already scaled, it should be fine. I don't see why this would be trouble. If it tries to scale it again, whatever. Maybe it does something intelligent on the inside. So normally, you get all these scores. numpy.random of 10. You got a bunch of scores, say. Suppose these were your scores, output from your logistic regression. Your logits, so to speak. You're just like, oh, that's interesting. maybe I believe it's class 4 because this one is kind of higher. But you're like, oh, but I'm not sure how much higher. So softmax just scales all of these so that none of them is greater than 1, none of them is below 0, and together they all sum to 1. And the easiest way to do that is to raise them all to an exponential. So let's say soft scores equals numpy.exp of scores divided by numpy.sum of numpy.exp.scores. Yeah, okay. So I take the exponential of every term, so e raised to whatever that value is, and you just divide by the sum of all those. So basically when you raise them all to the e, then you just ask, what share of all of them do they have? So you could instead, for example, scale by just asking, well, what share do they all have? But some of these, they could be negative, there could be other things that are screwing you up. Just make sure that they're all positive, they're all less than 1, they all sum, and together they all sum to 1. It's important that they sum to 1 because you need to be in one of these classes in this kind of classification problem. So if we plot soft scores, you'll see this. There we go. You notice this looks exactly the same when we plot it, because it is the same. It's just now, well, this one's at like 15%. 15% probability. Well, now you can be pretty sure that that's not actually that interesting, which these are just randomly generated numbers, so that's what you expect. So what I don't see is the sparse part of this equation. Where's that coming into play here? Sparse, softmax, there we go. Oh, no. Let's get some actual, here we go. So where is it sparse? Sparse, softmax, cross entropy. I mean, normally you say sparse when mostly you're dealing with zeros. Oh, I guess it's considered sparse because when you take your labels and convert them to one hot format, you only get a 1 in one position, and most of your array is in zeros. So you can store that matrix in a sparse format, and then it makes a lot of computations easy. So this calculates how wrong you are, and the way it actually does this is you convert your logits, your scores, over to this soft scores, and that's sort of probability. Now you've got 10 of these, and you take the, make sure I do this right. Actually, I want to make sure I look this up. I believe you just take that and dot it with the actual label. So you take whatever probability that you have the correct label. Implementing regression training, softmax regressions, evidence, softmax, implementing placeholder variable training. Here we go. Yeah. Yes. Okay. Okay. Yes. You've got your predicted probability. What is this? Times the log of that. So you're measuring the entropy. And so this is just sort of an approximation to something else that I'm not going to get into. So we can implement our cross entropy. Oh, it's y prime log of y, excuse me. Oh, doop-de-doop. So y prime is the correct label, and log of y is the predicted probability. So you take the log of your predicted probability of the one that's correct, essentially. And that's what you're adding up. Yeah, there we go. You do that and then reduce mean. This just says, hey, you've done it on this many batch size images. Let me just add those up. Or no, reduce mean says, let me average all those. Interesting. So if you get one really wrong and one spot on correct, those will kind of average each other out a little bit. Except you're taking a log of that probability, so you're getting burned no matter what. And then you get that loss function back. So you get some number out of this. So you got a number that says about how correct you were in a statistically responsible way. I'm definitely sticking with that. So what do you do with that? You take that number and you say, given a learning rate, I will correct my model this much. I will fiddle with my weights a little bit so that I can improve this loss appropriately. Or another way of thinking about it is, this loss I can compute using calculus comes from certain errors and certain weights. I will adjust those weights using that error, and I will move them in the appropriate direction using my learning rate to scale that. This also creates a summarizer. So it creates a special TensorFlow object that'll keep track of the loss over time if you ever get TensorBoard working. I've never gotten TensorBoard working, so that's not a problem for me. Okay, creates an optimizer. We're going to get into that. Creates an op. We're going to get into that. Let's just jump into the code. That's more fun. tf.scalar summary. This is what just logs some information. It says, hey, save off whatever the name of our loss operation is. You might recall we gave that a name, x entropy. Oh, excuse me, no, x entropy mean. And you save off the loss. So at every iteration, you're going to be saving off. Every time you call this function, you'll be saving off this loss to this object. Optimizer, okay, here's how you actually optimize. So gradient descent is one of the sort of the most simple optimizers out there. All it does is it looks at your function. Suppose you just got a generic function, say numpy.random 10. Seriously? numpy.random.random. There we go. You got some generic function. Let's do more. There we go. Oh, that was way too much. Okay. Numpy has no attribute range. A range. There we go. Okay, suppose you've got some function, for example. Excuse me. And you're trying to get to one of the peaks in your function. In our world, this peak is going to be, or you can think of it as a trough. Let's look at the trough, because it's called gradient descent. You want to get to this trough. You want to get to a minimum loss, which is a very good model. It's relatively accurate. So if you're in a particular position on your model, you'll say, well, I want to move down, right? Problem is, you don't have the full picture of your model. You're only looking at maybe one place. What if you look at some other places too? So gradient descent sort of tries to compute the derivative of your model at a particular location and says, okay, I've got a derivative, so you should start moving down is that way. So move in that direction. The problem being with your neural network, it's not a simple function of one variable. It's a function of thousands of variables, potentially. Every single weight is a variable. So you're in a very, very high dimensional space. It's no longer easy to visualize or even tell what's where. So gradient descent computes, okay, move a little bit in this direction on all of these variables. And you don't have to compute the gradient yourself. That's what the optimizer here does, that given your TensorFlow graph. And you're going to move a little bit in the correct direction towards this trough. Or you might be going towards, for example, you might really want to get to the global minimum. You might end up in the wrong, a local minimum over here. So you need to be careful that you don't end up in one of these. You don't get stuck here. So your learning rate shouldn't be so large that you end up, say you start over here on the left, that you jump way over here. You say, I need to move down. Okay. To move down, I need to increase this variable. All right, increase it a bunch, and then you end up here. Then you need to go down again, you end up over here. and you end up over here. Really, you just wanted to get over here. You only needed a small change. So generally we say use a small learning rate such that you don't jump over like that. And that's a hyperparameter that you can fiddle with. All right, another question. Someone has a value shape error. Must have rank 2 star. This happens after the second max pooling layer is provided in a 1D array from the previous layer. Yes, Nomad Jake. You've got a value shape error because you have a max pooling layer. Yes, you did max pooling on a one-dimensional array. So you've got sort of one-dimensional output of that. But your next layer must be expecting a two-dimensional input. If it's like, for example, a convolutional neural net, you're going to have to feed it either a two-dimensional input or use a one-dimensional convolution. tf.nn.conv. Yeah, you can tell it, I think. Input, filter, strides. So by default, it defaults to a 2D convolution. But you can just make one of these, I think the strides. You can just make the strides, I believe. I might be wrong. Oh, must have strides 0 equal to 3 equal to 1. Yes. Yeah. This is like your x stride and this is your y stride. So your x stride is just going to be 1 or 0. Because you might not be moving at all in that direction. It would be nice if they provided a proper 1D convolutional operator. Anyway, so that's the optimizer here. Gradient descent optimizer. With the prescribed learning rate, probably something like 0.01 or 0.1. Something like that. Global step. Okay, so given that this is our optimizer object, what is this? Create a variable to track the global step. Oh, this just says how many times have we trained this model? How many times have we moved this model at all from its initial variables? How many batches have we run? Which I wish they defined step better when they make this. It's how many batches have we put into the data? Trainable equals false. Yes, so this is a variable. We're going to change it, but we're not going to train on this variable. We're not going to try to optimize the global step number. Okay, train up. Optimizer.minimize. So this is the function we actually say, given this optimizer or gradient descent with a particular learning rate, and knowing that we're on this particular step, minimize this value, loss, by fiddling with all those weights. By fiddling with all these weights. I'm starting to lose my voice. This is trouble. Okay, we're almost there though, almost there. And then you return that train op. So train op is now some funky object. And what it's done is it's modified those weights inside your graph because they were TensorFlow variables, and you can do that. All right, finally, evaluation. So this is where you're just going to learn how good was our actual model, given our scores for the model and the actual labels for the model. Note that this is the same as our loss. Takes the same inputs, but evaluation is going to return to us an actual accuracy. And the accuracy is different because to compute the accuracy, we're just going to be looking at our logits, and we're going to ask, is our biggest one, we're not even converting the softmax, is our biggest logit, is our class with the highest probability the correct label? We don't care how high it is. Could be 20%, could be 99%, just is it the highest? And we're saying in this tf.inTopK business, I haven't looked this up, but I can tell how it works already. Give it this list, compare it to this list. Actually, no, I might need to look this up. inTopK. Interesting. Oh no, the labels are the actual labels. Right. Is the index at this label of logits, so is the score for 1, say, if 1 is the correct label, is that in the top K, where K is 1? Is it the top one? That's all. But again, the catch is, this doesn't care how correct you are. You could just barely be correct. You could have, this is an 11%, and all the others are like 9.9%, and it would still work. I guess 10.9 and 9.9 for the others. And then all you do is you add up how many times you were correct. That's all this reduced sum was. Reduced sum just says add up these numbers. And we're casting this to a 32-bit integer because I think this might return floats by default. Doesn't really matter. Is this... So this is going to give you a number of true entities. So it's not giving you a percentage correct accuracy. Let's actually run this now. Main. Missing one operand for positional argument. Yeah, let's just run that. Oh, let me kill that. Let me just run this real quick then. So we're extracting, we're training it using 900 sets. It says, your precision is 86%. That's not too bad, but that could be better. Let me train it for another 900. And it spits out and says, yes. Using 5,000 on the validation, we get 90%. On the testing data, we get just 89%, which is pretty miserable. Not miserable. It's much, much better than just randomly guessing. But you can do this good with a simple logistic regression model, I think. So that's mnist.py. It's, again, excruciating detail that I just walked through that, and I realized there's not a whole lot of action on the IPython side of things. And this uses up a lot more of my voice as I'm just talking, explaining, as opposed to saying, what's this? But that was mnist, and that was fully connected feed.py. So with both of those, you can build the full mnist digit classification model. To do something stupid, you could modify inference here and add your own layer. So you can insert your own layer, say, here. So then you could have one with 3 hidden layers. You would just need to update the function call with hidden 3 units, and you would need to update your final layer linear to read hidden 3 units instead of hidden 2. And to actually use hidden 3 units instead of 2 here. I mean, you can do plenty of other things. There's a million examples of this. So I think that is going to be good for this, for yet another line by line. Keep the questions coming. If you have a particular tutorial you want me to bang my head on in whatever software, if it's TensorFlow or if it's Keras or Theano, send me an email, let me know. I would be very happy to take a look at that and bang my head on it. And my voice is just about giving out, so I will definitely give it a break. You guys have a good night, and keep on data mining.